Okay, in this video, we're going to start talking about matrices as mathematical objects in and of themselves. We're going to start to talk about how to combine matrices. So we'll talk about adding. We'll talk about what's called scalar multiplication of matrices. And let's just start by, let's consider a matrix A, which is going to be the matrix 3, 1, 4, 1, 5, 9. So here we have a matrix that has 2 rows and 3 columns. We say that A is a 2 by 3 matrix. So it's always the number of rows that go first, the number of columns that go second. Okay, so A is a 2 by 3 matrix. In general, if A and B have the same size, so if so when I say size, what I mean is 2 matrices have the same size if they have the same number of rows and columns. They're both 3 by 5 matrices, or they're both m by n matrices in general. But if A and B have the same size, say, what I mean by that again, let me just write it. It's the same number of rows and the same number of columns. Then you can define A plus B as going to be the matrix where, so this is the matrix obtained by adding, so obtained by adding the corresponding entries. So by adding the corresponding entries. So what I mean by that, let's just do an example. Let's say that we have A, which is this matrix above here. So a little iPad magic, we're going to cheat. So let's say we have A and B. And B is going to be the matrix 1, 2, negative 1, 3, 0, 1. Then A plus B is going to be the new matrix. It's going to have the same size as the previous ones. And what we're going to do is we're going to add the corresponding entries. So we're going to take 3 plus 1. So we're going to take 3 plus 1, add them up to get 4. 1 plus 2 is 3. 4 plus negative 1 is also 3. 1 plus 3 is 4. 5 plus 0 is 5. 9 plus 1 is 10. So that's the matrix A plus B. Okay, so that's how we define the sum of 2 matrices. And really, that's all there is to it. If 2 matrices are not the same size, you can't add them. Addition of matrices is only meaningful when you have 2 matrices that are the same size or same order. So sometimes instead of saying size, sometimes people say order. That's it. That's really all there's to talk about. There's also scalar multiplication. And this is multiplying any matrix by any scalar. When I say scalar, this will make more sense as we go along, but when I say scalar for now, I just mean real number. So I can multiply any matrix by any real number that we want. So for example, if I were to have A is, let's just make it a square matrix, 3, 1, 0, 4, then 5A is going to be the matrix where we take each value of A and multiply it by 5. So we're going to end up with 3 times 5, 1 times 5, 0 times 5, and 4 times 5. So the matrix 15, 5, 0, 20 will be 5A. So that's scalar multiplication. And once we have addition and once we have scalar multiplication, we can combine those. And for example, if I were to take, let's say A is this matrix again, and B is the same matrix that we worked with before there. So if these are our 2 matrices, then we can do things like talk about A minus B as being A plus minus 1 times B. And here we're just relying on the fact that we've defined how to add two matrices, we've defined what it means to take a matrix and multiply by a scalar, and then we can combine those, and we get exactly what you think. You would get A minus B, so 3 minus 1 would be 2, 1 minus 2 would be negative 1, 4 minus negative 1 would be 5, 1 minus 3 is negative 2, 5 minus 0 is 5, 9 minus 1 is 8. Okay, so that's how we could do things like A minus B. We could also do things like 2A plus 3B, where what we do is we take 2A, and so I'm going to just write out first what's 2A and what's 3B. So I'm going to take each entry in A and multiply it by 2, and we're going to end up with 6, 2, 8, 2, 10, 18. And for B, if we multiply everything by 3, we're going to end up with 3, 6, negative 3, 9, 0, 3. And then we can combine these, and we end up with 11, 8, 5, 11, 10, 21. Shouldn't take me so long to add. Let me just double check. Yeah, no, I can't add. Small disclaimer, trust my linear algebra skills, don't trust my addition skills. All right, 6 plus 3 is 9. There we go. That makes me feel better. 6 plus 3 is 9. 2 plus 6 is 8. 8 plus negative 3 is 5. 11, 10, 21. Okay, so there's the 2A plus 3B. There's that quantity. This quantity, by the way, has a name. So given matrices, or really given any objects, but we're going to specifically talk about it with matrices, A and B and C and D and so on. The quantity, if I were to take, say, a constant, say C1 times A plus C2 times B plus C3 times C plus C4 times D and so on, that's called a linear combination. So this is called a linear combination of A, B, C, and D. So this quantity 2A plus 3B is called a linear combination of A and B. Okay, so whenever we say linear combination, we mean a combination like this. This linear, by the way, I should add, is the linear in the sense of linear algebra. Okay, so we'll talk about exactly what linear means as we go along. Let me just make sure that we're clear that that's the word linear. Okay, so this is linear in the sense of linear algebra. Okay, so we'll talk about that much more soon. Well, not soon, but in chapter 4. Okay, so that's a linear combination. So from this, we can do things like, let's write the 2x1 matrix. So let's write the 2x1 matrix 5, 6 as a linear combination. So as a linear combination of the columns of our matrix A, which is 1, 4, 2, 3. Okay, so I want to write 5, 6 as a linear combination of the columns of A being 1, 4, 2, 3. So what I really want to do then is I want to find constants C1 and C2 so that I can write 5, 6. We can write 5, 6 as C1 times 1, 4 plus C2 times 2, 3. And how do we do that? Well, we know how to multiply any matrix by a constant. We know how to do this scalar multiplication. So this means that 5, 6 can be written as C1 and 4C1. And the second matrix can be written as 2C2 and 3C2. We know how to add two matrices, so let's do that. So that means that 5, 6 is going to be written as C1 plus 2C2, and 4C1 plus 3C2. And I want you to notice that even though the column on the right here, so even though this matrix looks a little different because it's got more stuff in it, it's still a 2 by 1 matrix. These are all 2 by 1 matrices. Okay, 2 rows, 1 column. All right. So we want to find constant C1 and C2 so that this is true. This is an important, and I'm going to say this, and this is going to sound possibly silly, but it's actually quite important. Two matrices, A and B, are equal if and only if A and B have the same order, have the same size, and all corresponding entries are equal. Okay, so certainly if two matrices are of different sizes, they're not equal. But even if they're the same size, if they have different entries anywhere, they're not equal. So to be equal as matrices is actually a very strong thing. It means that each of the corresponding entries are equal. So in our case, we know that 5 has to be equal to C1 plus 2C2, and 6 has to be equal to 4C1 plus 3C2. And then how could we find these constants C1 and C2? Well, this is exactly what we did in the previous videos in chapter 1. We solved systems of equations. So here we have 2 equations and 2 unknowns. And what we can do is we can turn this into a augmented matrix. And the first thing to do to turn it into an augmented matrix is actually move the equations to the right. So again, a little iPad magic. I'm going to move these over to the right. And from this, what we can do then is we can form an augmented matrix. So our augmented matrix that we're going to look at, that we're going to try and simplify, is 1, 2, I put a dash there to represent the equal signs, and 4, 3, 6. And so the idea is we want to get the left side to look like 1, 0, 0, 1. If we can do that, then whatever we end up with over here is what we get as our solution. So that's our goal. So let's go ahead and do that, and that'll finish our video. So we want to simplify this augmented matrix. So the first thing that we can do is we're going to replace row 2 with row 2 minus 4 row 1. There's lots of ways, by the way, to get to the right answer. But the way I'm going to do this is we're going to replace, oops, I didn't mean to copy row 2. Row 1 we can copy because we're not adjusting it. We're not doing anything to it. We're using multiples of it to add to row 2. Row 2, our new row 2 is going to be 0 by design. That's why we picked minus 4 row 1. And then let's see, minus 4 times 2 is negative 8, plus 3 is negative 5. And then negative 20. So negative 4 times 5 is negative 20, plus 6 is negative 14. And so from there, what we can do is we can take row 2 and multiply by negative 1/5. And if we do that, we end up with, again, I'm going to leave the top the same. So 1, 2, 5, 0, 1, 14/5. So just dividing each value in row 2 by negative 5, we end up with 0, 1, and 14/5. This already tells us, if we want, we can stop here. This already tells us that C2 is going to be 14/5. And so you can either do the matrix manipulation to solve for C1, or you can just remember what this augmented matrix does. And so just whatever you think is easier, always do what you think is easier here. You can either simplify the matrix a little bit or just use the information in an equation, which is what I'll do. So we know that C1 plus 2C2, C2 being 14/5, must be equal to 5. And then from there we can solve for C1. This means that C1 is going to be 5 minus, let's see, 2 times 14 is 28, so 28/5. 5 is 25/5, so that's -3/5. So it turns out that we can write 5/6 as C1, so -3/5, times, I need to go back and look here, 1/4, so the matrix 1/4, plus C2, which we found to be 14/5, times 2, 3. Okay, and so we can indeed check that that all works, that that's all fine. Okay, so there we've written our matrix 5, 6 as a linear combination of the columns of A.